All right, so let's look at this first one, and then I'll give you time to do the other three so we can practice it, just so that we have something to kind of guide us instead of staring blankly at it. So for this first one over here, y equals x squared minus 2, I know it's small. What is our degree on this one? 2. Our degree is 2. It is the highest exponent that we have on a term in the equation. What is our leading coefficient? 1. It's the number in front of that highest degree term. So our leading coefficient is 1. So what are the maximum number of zeros we could have for this function? What's our maximum number of roots? 2. Our degree will tell us every time the most solutions we can have. So this could have 2 real roots. The fewest number of roots can have depends on whether it's even or odd. Because even functions, we think about our parabolas that we were working with last chapter, I can have no real roots. It can never cross the x-axis. So even degreed functions do not have to have real zeros. It might have 0 real roots. If we have odd degreed functions where our arrows go in opposite directions, I have to have a root somewhere because my arrows point in opposite directions. I cannot avoid the x-axis if I can go up forever and down forever. I have to hit something. So odd degreed functions have to have at least 1. Even degreed functions might not have any. So our next box down is looking at that end behavior, and we need to be really careful because they've got our x's flip-flopped from the way that we had them yesterday. Our right arrow on this one is this guy. So we always need to start with looking to make sure we know which x is which arrow. As x goes to positive infinity, that is our right arrow. So for this function, that right arrow is going to point which direction? Because we have our positive leading coefficient, since our leading coefficient is positive 1, this is going to go to positive infinity. Our right arrow will always match the sign of our leading coefficient. Is our left arrow going to match, or is it going to be opposite? It is going to match. We use our evenness versus oddness for that. So our degree, we care about whether it's even or odd. Our leading coefficient, we care about whether it's positive or negative. So for our right arrow, we know that that's going to be positive. And our left arrow, we know is going to match because we're even, so it's going to be positive. So my left arrow goes up, and my right arrow goes up. For our little thumbnail sketch, that just means we're catching a vibe as close as we can. I know my right arrow is going to go up. I know my left arrow is going to go up. I can have at most 2 roots. I don't have to have any. I could just connect this up as it is. Just go whoop, ta-da. That would work. I could have this be here. I could have this have no real roots up here. Totally valid. The one thing we don't want to do is something like this because that has more than 2 roots. We can have at most 2 roots. That one has 4. So don't go above the maximum. If we have more information, great. If we notice that our y-intercept is a part of our equation, great. But you don't have to at this point. Questions on that first one, or have we got any of those pieces? Okay, now that we kind of have a guide for what we're doing, try the other 3. So it talked us through the first one. Try the other 3. I'm going to give you guys a couple minutes to do that. We've got some time. give these a shot. Because honestly, this is very, very much like question number 1 on that first homework. A, B, C, and D are just like this. And honestly, half the back could be done like this too. All right, so on this second one over here, what's our degree? 3. What's our leading coefficient? -1. What are the maximum number of zeros we can have? What's the highest amount? 3. It's always going to be our degree. What is the fewest amount of zeros this is going to have? 1. Odd functions, when they're pointing in opposite directions, have to hit the x-axis somewhere. They have to. So when we're looking at our end behavior here, which way are our arrows going to point? So our right arrow always matches the sign of our leading coefficient. So our right arrow will point down. We'll go down to -infinity. Because that leading coefficient is negative. Our left arrow is going to point which way? Up. Because we have an odd degreed function, it's got to go the opposite. So my left arrow is going to point up. My right arrow is going to point down. We're going to do a sketch that has no more than 3 roots. So I could draw it like that. That has 3 real roots. Great. I could draw it like this. That's got 1 real root. I could do something like this, which has 2. There's lots of different ways we can draw this. But it's going to look vaguely that-ish. Questions on that one? All right, what do we got on the next one? What's our degree? And our leading coefficient? 1. So we have an odd positive here. Degree is what we're looking at for evenness versus oddness. Leading coefficient is positive versus negative. So we are an odd positive here, which means we already could do our end behavior from right there. What is the fewest number of roots that this could have? 1, because odd functions always have to go through the x-axis at least one time. What is the most number of roots we can have? 5. Which way is our right arrow going to go? The right arrow will not go down on this one. So if we look at our right arrow, that's this bottom one here. The right arrow is always, always, always going to match leading coefficient. So is this positive or negative? Positive. So the right arrow will go to positive infinity. So our leading coefficient tells us which way the right arrow goes. They have our right arrow on the bottom here. So x goes to positive infinity. That's the right arrow. Because if I stood in the middle of my underline here, positive numbers are to the right. Positive infinity is the right side. Is our left arrow going to match or be the opposite? Opposite, because we have that odd function. So since I know my right arrow is positive infinity, my left arrow has to be negative infinity. So when we're making a little sketchy sketch, bless you, my left arrow goes to negative infinity, means it's going down. Right arrow goes to positive infinity, is going up. As long as I have no more than 5 roots, I can sketch this with whatever creative choices I want. So I could go 1, 2, 3, 4, 5. Ta-da! That one's totally an acceptable sketch. I could go like this. It has 1 root, absolutely valid. I could try and make any number of roots that I wanted. That one has 2. This one has 3. I can make any connection as long as I don't do that has way more than 5. Don't draw a sketch like that because the maximum number of times you can cross my x-axis is 5. That's a lot more than 5. So this is bad. Anything 5 or fewer works just fine. I can have 5. 1, 2, 3, 4, 5. 5 is most. So we have a lot of choices with it. We can do 1, we can do 2, I can do any combination up to 5. We at this point do not have the information we would need to be more specific than that. Questions on that one? Okay. Last one on here. What is our degree? 4. It's our biggest exponent. What is our leading coefficient? -2. It's the number in front of that term. So is this one even or odd? Even. Our degree is what we look at for that part. So is it positive or negative? Negative. So we're looking at an even negative function here. So degree we care about even or odd. Leading coefficient we care positive or negative. That tells us all the things we need for our end behavior. When we're looking at our zeros, what is the fewest number of solutions this might have? 0. I can have no real roots. If I have an even degree function, if you think about our parabolas, I can have that thing not touch my x-axis at all. Whether it's pointing up or pointing down, it does not have to hit. It can avoid. What is the most number of roots we're going to have? 4. It's our degree. Every single time. The maximum roots we can have is the degree. So if we're working with these and I wound up with 6 answers and our degree is 4, something went wrong. Looking at our end behavior here. Which way is my right arrow going to go? Down. Right arrow always matches that leading coefficient, so it's going to go down to our negative infinity. That negative is what we care about right there. So my right arrow is going to point down. Which way is my left arrow going to point? Also down, because we have an even function here, which means they need to be matchy. So it's also going to point down. So when we're looking at making ourselves a little sketch, I know my right arrow points down and my left arrow points down. We're going to connect it up as best we can. I can have as few as 0 roots, as many as 4, so I can't go over 4. So it might look something like that. I could do 1, 2, 3, 4 real roots, like that. What we cannot do is that. That's way more than 4. So I could have 2. I could have 1. I could have none. I could have 4. As long as I don't have more than 4 roots, we are good. And that's as close as we have right now. Questions on these? Because this is essentially what question number 1 is on that first homework. If you do this, you have more than enough information for question 1. And 2, honestly, you could do that way too. And it's working backwards through this for question number 4. So honestly, this covers a good chunk of homework 1. We are going to practice just a smidge more with these. We're going to do 2 more from our notes packet, and then we're going to look at the next concept. But questions on these 4. I know this was a whole lot up here. Then let's look in our notes packet. Page 5. We already did A yesterday, so we're going to look at B, and then I think we're going to do, the other one I have is D. So we'll do those 2 on the right. And we're going to practice this. And it's honestly pretty much the same thing that we just did in the bell work. We're just going to have this in our notes so we could look at it later if we need to. Oh, snap live. So for this one here, we're going to do the same thing pretty much. What is our degree? Not going to be 6. I see why we think that, but we just want the biggest. 4. So it's just whatever one is the biggest. What's our leading coefficient? 1. It's the number in front of whatever that term is. So we've got a positive 1 here. Which means, is this even or odd?
Odd. I mean even.
Even. Is it positive or negative?
Positive.
Positive. So we're looking at an even positive. Got it? You too? So even positive means I know what happens to my right arrow. Which way is my right arrow going to go? Up. It's positive. So my x going to positive infinity means my f of x, my function, is going to go to positive infinity.
Would it be the opposite now? Because, I mean, no, because even is always the same, odd is difference.
Evens match, odds are opposite. So since we know they're matching, they're even, which way is my left arrow going to point? Up. They're both pointing up. So our leading coefficient tells us the right arrow. Our evenness versus oddness, so our degree, tells us what happens with the left arrow. This one tells me it's going to match. And what is the most number of real roots we can have on here? It's going to be 4. So I know it doesn't specifically tell you to sketch in there, but I'm going to sketch it anyway because it's good practice. So I'm going to make ourselves a little sketch here. I know my right arrow points up. My left arrow points up. We can have at most 4 roots. We're going to connect it up. We're going to do as best we can. The only other information we have even at our disposal is our y-intercept is always going to be the constant at the end. So we would have a y-intercept at 4. I'm not going to be petty about if we put that on our sketch or not. If you struggle with the fact that we don't have any other points, that's one thing you can use. But you don't have to. Like, I'm totally cool with us not. We're going to connect it up. We're going to make sure we do not have more than 4 roots. And we're going to call it good. It's a sketch. Getting a sketch is getting the vibe of a graph. It is not getting a beautiful, we can read the values and solutions off of it kind of graph. We're getting as close as we can to calling it good so that we have a mental picture to look at. Okay. On homework 1, the back side of it, sometimes you're given just the picture, and we can figure out our leading coefficient from the right arrow. I can figure out if it's even or odd from how it matches, or if it doesn't match. And we're going to count how many roots this has. This one has 1, 2, 3, 4 roots. So that's what the back of homework 1 is looking at, is it's giving you the sketch, and you're going to piece together the pieces we can. Let's do one more of these. We'll do D, and then we'll look at the next page. Just because we've now done, this will be number 6 of the day of this kind of question. So we're going to look at D. It's the one directly below the one we just did. There's nothing wrong with the other ones on the page, like absolutely fine. Just kind of covering what we can. Yes, dear. Mm-hmm. Correct, for the right arrow. Because here we have our degree is what? 2. Degree is our highest power. And our leading coefficient here, -1. That number right in front. So we've got that negative leading coefficient. And we have our degree being 2, which is another even. So when our leading coefficient is negative, that tells me what happens on the right arrow. When x approaches positive infinity, that's going to match my leading coefficient. So my right arrow is going to go to that negative infinity. Right arrow always matches our leading coefficient. The right arrow matches the leading coefficient. Our right arrow is when x goes to positive infinity, because positive numbers go to the right. My left arrow, which way is that going to go?
Negative as well.
Negative as well. Even functions are matchy-matchy, because they can't even do anything different. Oh my god. Evens are super matchy. Odds, opposite. Odd ducks go to the disco. So, what is the most real roots we can have on this one? 2. I mean, this one is a quadratic. We could go wild and try factors and things, so snap what. We have tools to do this. We've dealt with quadratics before. But we don't need to. We're getting a sketch. We're working with polynomials now. I know my left arrow points down. And my right arrow points down. Just matching my colors. I could have 2 real roots. I might have no real roots. If I have 2 real roots, it looks like this. If I have 1 real root, it looks like this. If I have no real roots, it looks like this. Any of them count as a valid sketch. If we catch the fact that we have a y-intercept at positive 11, we'll look kind of like that. But at this point in this chapter, that's as far as we're going to go with our sketch. We're not going to try and find our roots like we did in the last chapter. It's a lot. It's complicated. Annoying even. But we could. I could try and factor that. I could put things through the quadratic formula. All those pieces. But this gives us a kind of overview sketch of it. As we work through this chapter, we're going to work on getting more and more and more precise on how we graph these. And getting more and more precise about our details. So as we work through these, they're going to get more and more and more picky and more detailed. So what we're going to look at next, we're going to look at the bottom of page 6. And we're going to do just the first example. And I have a billion things up here on the screen. This is the bottom half of page 6. So these top couple lines here, this is what the tool we're going to use. We're going to use something called the location principle. And what that is if we have a polynomial, and we're either given a table or we make a table and are looking at values. So we've picked x's, we've substituted them into our equation and gotten y values. This is like an xy table. A lot of times we give them to you sideways because they fit better on paper. It can be sideways or it can be vertical. It does not matter how we draw our tables. But if we have a y value of 0, that's when we have a root. That's our roots, solutions, x-intercepts, zeros. If y is 0, it's 0. Sometimes we don't get zeros in here. We would like to try and find solutions on this, but I didn't get any y values of zeros with this particular equation. They have taken this equation, our f of x equals x to the 4th minus 2x cubed minus x squared plus 1, and substituted all these values in to get these y values. This equation gives us these y values. So what we want to know is we want to know where we might have solutions here. And we can tell this by either graphing the points as they are, or we can look at the table and see if there is a sign change from one value to another. So look at our y values and see if we have a positive to a negative or a negative to a positive. If it changes signs, so if we have like a -1 that goes to a +2, somewhere between these 2 points, I have to go through my x-axis. I have to. So there will be a root between them if I have a positive value and a negative value. So if we look at this table here and we look at our y values, do we see any places where it switches from positive to negative or negative to positive? Where? Yes, and we're looking at our y values. We want to care when the y values change sign. Yeah, over here, between our x of 2 and our x of 3, because we go from -3 to +19. Absolutely right. Right here, we have switched from negative to positive. That is a change of sign. So when my x is 2, it's going to be below my y-axis. When my x is 3, it's going to be above. Somewhere between, I have a 0. When we're listing these in our possible zeros, we did this with quadratics, we're going to list using our x numbers because a 0 by definition has a y of 0. So we know that between our x of 2 and our x of 3, we're going to have a 0. We're going to have a root. Is there another place where my y values change sign?
0 and 1.
Between, yeah, between 0, 1, and 1, -1. I go from positive to negative. So positive to negative. So when my x is 0 and my x is 1, between those two I should have a root. We have a 4th degree polynomial here. So are my arrows going to match or are they going to be opposite? Match. Our degree is 4. Even. So they should do that. Are they going to point up or are they going to point down? Up. Because we have a positive leading coefficient. So those parts are still a part of this. We have our even degree. We have our positive leading coefficient. So I know my arrows should point up on both ends. What is the most number of roots this could have? 4. It's still our based off our degree. I could have 4 real roots, and I know that's above your table, and I have it below mine. Formatting's fun. So I could have 4 real roots. I could have no real roots. In this table, I see I'm going to have 1 root between 2 and 3 and 1 root between 0 and 1. What we're going to do to make this sketch, and it's going to be a slightly better sketch than the ones we did in the bell work, is we're going to plot the points as best we can. Some of these ain't going to fit. I'm looking at you, 4. Ain't fitting, for sure. You can count by ones. These ones are unnumbered graphs. You can count by ones. You can count by twos if you want to fit more pieces on there. I'm just going to count by ones on this one because I'm not going to fit 29 or 19 on there. When we have points that are off the graph, you can just draw an arrow to it. So for like -2, 29, that's going to be way up there somewhere. Yes. -2, I've got 1, 2, 3, 4, 5. 29 is going to be about where the ceiling is. It's up there somewhere. We've got -1, +3. I can reach that one. It's right here on my graph. 0, 1. 1, -1. 2, -3. 3, 19. Whoop, that's way up high and off my graph. Almost at the ceiling again. And then 4, 113, I believe we could hit with an airplane. That is way up. That is not fitting. So by plotting the points we actually have already matched the end behavior we expected. We see even, our arrows are both pointing up, and they're pointing the same direction. So my end behavior is included in there. Always a good idea to double check it and make sure we don't wind up with things that are like weird happening on the outside. It's a good way to kind of spot check. We're going to connect up the dots we have and get as close as we can. So I'm going to take it from an arrow through the points we've got, connecting to this other arrow that I know has a point way up there. And we can see between 0 and 1, we have a root. Between 0 and 1. That's what we said. It switched from positive to negative. Switched from positive to negative, so I have a root in between. I have between 2 and 3 a root. We switched from negative to positive, so I have a root there. So by kind of doing a guess and check, picking x's to find y's, we can kind of try and spot some of our zeros. So we're going to work more with the location principle tomorrow, and we're going to practice on the next page a couple more of them. I don't want us to try and speed run one in the next 5 minutes, so we're going to stop right here. I'm going to put this up. Yes, sir. I have an answer for you.